to the first ever video of the self-taught software engineer. My name is Jacob, and I will be giving you the first introductory chapter into my course Programming Basics. Since this is the first video, I do recommend to watch like an even broader introduction into this whole channel and who I am. I gave this already in a different video. You should now in the top right corner of your screen see a link to that in the video, and I will also put it in the description of this video. And yeah, I will not give a grand introduction of myself right now, since that's what this other video is for. So let's jump right into it. The idea in this course is to, well, teach you, as you mentioned, the basics of programming. I structured this course to really start from the scratch, such that if you do have any prior experience with programming, then this is likely not for you, even though I can of course recommend to still give it a watch. I try to keep all the chapters like short and to the point, and of course depending on what you already know, you might still see some things that you didn't know beforehand, or that I explained hopefully in a better way than it was explained to you at an earlier point in time, such that you can still learn something out of it. Yes, the shortest intro I can give for myself is, yeah, my name is Jacob, as I mentioned. I was born and raised in Germany, so excuse my my potential German accent. And nowadays I'm living in the Netherlands, and as you might have guessed, I am working as a software engineer. And yeah, I would consider myself as being self-taught. For the most part, at least, but more of that in the other video I alluded to. And in any case, the point of this channel is to yeah, offer free educational videos to teach other people programming, software development, more engineering specific things and stuff like that. But let's jump right into it, so you're not getting any more bored. So, who's the audience of this course? As I said, you ideally, well, not ideally, I would say, but you likely didn't program anything beforehand. Otherwise, parts of this at least might be pretty boring to you. But I would say the audience are high school students that have a computer science or informatics course in their curriculum at school and want to, yeah, brush it up or even study for an exam with it or something like that. But of course, you can also enjoy these videos if you do not have these courses and have an obligation to write an exam or something. The other obvious candidates are university students, specifically first grade students that study something related to programming. Can be, of course, traditional computer science, but I know that nowadays for very many different studies, it is very helpful to know the basics of programming and being versed in that. So I think that's good. But also, of course, here it goes, you can study pretty much anything. And that leads very nicely into my last point. Honestly, this course can be for anyone that is interested in programming. It doesn't at all have to be for high school students or university students. You can be even younger or a lot older or anything in between. I don't care. This course is just, I'm trying to teach you from my perspective as how I came to do what I'm doing nowadays, which I enjoy very much, which is yeah, writing and building and creating software. Yeah, from the point where I started, at some point where I was also starting from scratch, obviously, and didn't know where to start. I was very confused what was going on. And looking back at this, I'm trying to make this a bit easier for other people. Not only, but to an extent specifically for people that do not go through like the traditional, or well, not necessarily traditional, but that don't have a formal education of computer science. Since yeah, I can go into a bit more detail why that is in a second. What is the objective of this course really? So first and foremost, it's important to me that you take this quote to heart here in the top right, from each according to their ability to each according to their needs. So you're free to skip any chapter. That's a nice thing of this, right? We're not in a university or school setting. Skip whatever you feel like skipping, watch whatever you feel like watching. I'll try to make it interesting. I'll try to make it understandable. And as I said, I'm trying to approach it from a perspective where you might not come from a background where you do know all sorts of things already. Later on, my plan is, and you're going to hear that also in the other video, my plan is to do other videos with a lot more advanced topics. But for this one, we're going to start from scratch. So yeah, go with the speed that you can. There's no obligation. That's really the point. Yeah, the thing that I'm trying to do here really is from the point where I came from until where I'm now, trying to teach you how I got there, because I would want, of course, that people that are interested in developing software to do just that, and teach them how to, and offer it in an approachable, open, and free of all sorts fashion. That does not necessarily require that you study a certain thing. And one thing I want to make clear here that I alluded to on the previous slide is that if you have your typical studies, which is most often computer science in university or also as a high school course maybe, specifically this first course that we're looking into here now, the first course that I'm producing, the programming basics, there's a big distinction that I quickly want to make between computer science and programming. Of course, that's why it's called computer science, which some people forget. Your university, you're not necessarily, that is part of the studies, of course, but you're not necessarily going there to learn how to program, to learn how to write software. It's a lot more things that are involved. That's why, after all, it's a university course and not like I know there's a lot of boot camps and stuff like that nowadays, but if we're talking about university computer science, which I think for many people at least is still the way to go after they finish their school education, and there's a lot more to that is, which why it has the science in the name, that we're not going to cover here. We're going to cover here, but in a less strict fashion. So this is really about more of the craft side of things. We're not going to be involved a lot, at least with academic topics. Of course, with scientific topics, certainly, because you do need them in programming as from a crafts point of view as well. But we're skipping on all the academia stuff you would do in something that has science in the name. And I'm not trying to claim here that this is scientific. It's hands-on. That's what I want it to be as well. Although the other side is also very interesting, and I can recommend that to everyone. I mean, yeah. So we're gonna start very, very easy with seeing why do we even program? Why should we care? Why maybe you're also watching this wondering what does that mean? I heard it from my friends. I'm thinking about doing it, or maybe even pursuing a job in that, but you don't even know what it is. Then things that the thing that is should be important throughout all of the chapters of this course and also other videos is terminology. One of the things that I was struggling a lot with when I was starting out, and you will still do that after years and years, but specifically when you're starting out, is that there's a lot of terminology being flung around everywhere, and you don't know what it means oftentimes. There's very many synonymous terms. There's very many terms that people use slightly different in slightly different contexts. Maybe people use it like slightly wrongly, just as upright, and they don't know it. You might get that in different countries. Terms are used differently. All sorts of stuff. I know this is true for pretty much any craft you can do. Every craft has a lot of terminology, but I feel in ours it's I wouldn't claim specifically a lot, because it's not like I know a lot of other crafts very well, but it's certainly a big problem that you get, which I think it's not that much for other crafts, is that if you try Googling for terms, you're gonna find a lot of results, because after all, yeah, it's computer related. So you're gonna find more than, let's say, for woodworking or something, which I'm sure there's a lot of glossaries and stuff, but you're not gonna find as many articles, I'm pretty sure. And that in itself can be very overpowering. Like if you hear something somewhere and start Googling it, chances are you find some very grandiose article about it that is nice for someone that knows what this term even means. but not so much for something that's getting started. So throughout this entire course, my goals also always is to touch upon the terminology a bit. And also I want to make sure that if you do not understand something that is specifically in that part, goes for anything with specifically terminology, don't hesitate to post in the comments to ask a question if something is not clear. What does this mean? I read somewhere it means this, but someone else told me this, but you get what I'm saying. We're going to quickly look into what does a programmer even do. This also is interesting since you see here there's a lot of different terms for programmer, software developer, blah, blah, blah. We're going to look into it in a second. What is a program even, right? What does that mean? What is also, because you also hear software, what is the difference? Again, going back to terminology, so you get this everywhere. This is the thing that you'll hear throughout me talking about it. And how is it executed? And then the majority really of the course is the building blocks of programming. One word here, I'm gonna try to keep it generally language agnostic, I'd say. Language agnostic in the sense of the programming language we're using. I will use for the later examples where you do need more than just pseudocode. So pseudocode being no language, just something you would scribble, like if you would do that. I will use Kotlin as for the sake of example, if required. Also for later videos, I'm planning that in entirely different courses, since I think it's a language that is very expressive and understandable and has some niceties that other expressive languages do not have. But more on that later. So that's the majority of the stuff we want to do, really. And of course, you should be able to take your first steps to write a few first small programs that do literally something. Compute something, print you out something. The options are endless, as you'll see after you jumped into it. And then once you did that, that you can jump into your first language. As I said, I can recommend Kotlin, but of course, if you have some specific needs, you want to do some specific type of application development that mandates using language X, then of course, that's ultimately the goal afterwards, that you have the general understanding of trying to read further material or watch further videos of this channel or any other channel, and being able to understand, hopefully, all of it if I did a good job. Yes, the materials we're going to use. So this is going to be, at least for this course, this does change a bit in more advanced courses I plan on doing later. Slides are going to be the major way of teaching the material. I'm going to try to make them plain, like they are here, not a lot of stuff going on. I try to put, if it does help in some way, some graphics and stuff, but I'm not trying to put like 100 million diagrams or photos or memes or something. I'll try to keep them simple, and that you can also refer back to them. I will always link the slides in each video description. They're public Google Sheets, such that you can go through them in your own time again, or even open them next to the video to click in your own speed, etc. The other thing, obviously, is I'm going to give many examples, because ultimately that's how you really understand something. Like throwing around a bunch of terms, even me giving like a formal explanation of them doesn't help oftentimes. What we're gonna do, not so much in the beginning maybe, but certainly later, is also live programming. I'm gonna just show you how certain things are done in an editor and execute them directly to see the results. Next thing is, if applicable, this is really depending on the chapter and on the course, some stories I have for my own side, how I learn certain things, if I can give some tips. Can be something funny, can be something educating, but yeah, something I experienced myself throughout my trajectory to become a software engineer. And then finally, if applicable, exercises. Here's a warning, of course, this is not a university course, so I cannot like grade anything or whatever. So if anything, I'll try to make exercises that are that you can either evaluate yourself to the best extent, or that I can automate in some fashion, that you can just run some piece of code and it tells you, hey, did you do the exercise correctly or not? This is, of course, a lot of work on my side, so I'll try to make them as nice as possible, but this is something that out of all the previous 4 points might be lacking the most, specifically in the beginning of this project. of this channel, since yeah, it does cost a lot of time. I'll try, but bear with me. Yeah, then let's quickly look into the curriculum, the chapters. So this is the introduction. We're not only going to look over what is what the chapters are, we're also directly going to jump into it in this video actually. So if all of this bores you, but you can also skip ahead already. I'll try to put these chapter marks into YouTube if I can figure out how that works. So it's not just going to be overview today, but also some hard facts already. Yes, then the first chapter is going to be program execution basics. So we're going to look into how does your computer, or any other computer for the matter of that, execute the programs you or anyone else wrote. Of course, that's why it says basic on a high level, because this in itself is a huge topic. For example, in a university computer science studies that takes multiple years, obviously, you're likely going to have entire lectures dedicated to just that, entire courses even. So we're going to scratch the surface, but to the point where you have the understanding that you need to understand what is going on when you do program. The next thing is going to be data types and type systems. I'm not going to explain now what it is, because otherwise I'm going to start rambling already. After that, we're going to look into, but only point I can make here is important to understand all the rest. That's why it is ordered, obviously. Next, the thing we're going to look into variables. So this is, I mean, you probably know variables and constants out of mathematics course. Don't worry, none of this is going to be mathematic in this entire course. Of course, we're going to do some arithmetic, like summing some numbers together, multiplying or whatever, but nothing where you require deep understanding of mathematics that goes over elementary school grade level. Then we're going to look at operators and expressions. So what does that mean is, if you did look already at some source code, and I presume some people probably saw some random source code already. I mean, you also, if you watch the news and they put like source code in the background if something got hacked, you know, these stock photos that after following this course you probably think like anyone else in the sector, like, oh my god, what are these stock photos? Not very accurate, but you see a lot of like characters being flung around, special characters on your keyboard being used for operations, and that's what we're going to look into, that how to use them, what they generally are. That does differ per language, of course, but there's some general ones that you pretty much find everywhere in some way or form. Yes, chapter 5 is going to be control flow. So what this ultimately just means is that depends a bit on the exact language you're going to use later on, but you're always going to have some sort of a notion of flow, meaning that your program has some starting point always. You need to kick it off from somewhere, and then it keeps itself running, right? That's ultimately the beauty of a program. You don't need to give it a kick every so often, as long as the program itself is running it according to what you programmed. Ultimately, that's all we do in this craft. It does certain things, and that is ultimately what control flow means, that you as the programmer control at an earlier point before running it. Actually, you control what it should do in certain situations, such that then later when it does run, it can just follow these instructions that you gave as a human, and and do whatever the program is intended to do. Then the 6th chapter is going to be basic data structures. Also, I'm not going to say too much about it, because it's otherwise a big topic in itself. Looping is the next one, which in essence just mean you have a collection of things. Literally can be anything, and you want to for each of the elements in your collection, you want to execute some sort of some sort of a task. That is ultimately what looping means, and we're going to look into how that works. And interestingly enough, for very, very many parts of programming, and I'm going to give some nice examples or anecdotes there. This is all you do all the time, like process lists or collections. The almost final one is going to be functions. So that just means how a mathematical function would work. So you give some input, you get some output out of it, and what actually happens with the input to arrive at the output is what the function does ultimately. So you're going to learn a way to compose your code such that you can reuse certain parts. Very easy example of this would be an addition operation. Let's say you want to add numbers A and B together. You're going to want to have that in a way that you can always repeat that. You don't have to write the entire way that you do that, but you can just use an add function, for example, give it the two numbers, and out comes your output, just as you know it from basic math operations. And finally, we all hope that does not happen, but it is sadly part of every program, errors and exceptions that can happen. And what we do, and it's an integral part of programming, what we do to mitigate them, that they do not happen, of course, but if they do happen, that you can handle them in a controlled fashion. Because ultimately what you always want to avoid is that your entire program just crashes. You all know from operating systems, they rarely nowadays, but they do occasionally crash, blue screen of death, etc. Ultimately, we want to avoid that it never comes to that point, and there's very many techniques how you can do that. All right, that are all the chapters. As I mentioned, it's basics, so there's probably going to be a follow-up course of sorts that goes into more detail on either a specific part, a specific chapter like topic, or just appends a whole other course at the end. I really want to start here from scratch. For people that never ever programmed before, that afterwards you have a basic understanding, and that you can then jump into more advanced topics, right? So that's it for the overview. As I mentioned, there's also already going to be some actual topics in here. So let's jump right into it with the introduction. So this is the actual chapter 0 if you want. So let's see. Why do we even program? Yeah? So that's the question we have to answer at the beginning before we jump into how it's done. So ultimately, the stupid easy answer would be we want to develop software. That's why we program. Of course, that doesn't tell you anything really. And so I have to make it a bit more precise. Just very quickly, so we don't lose someone already now. Software, if you did hear the term, I'm pretty sure, but if you're like a bit lost what it means, you generally have to distinguish between soft and hardware, meaning that hardware is something that your software runs on. The nice examples here on the right side, like an ADM that you all saw or used before, that would be hardware. So that's actually the machine, so to say, the physical thing that's running your program. And then software is just the intangible, that you cannot touch it, the thing that does control what the machine does in certain situations. So that is the stupid answer, develop software. What it really is at the end of the day really is a problem solving. That is like ultimately what you always do. You solve some sort of a problem, and don't understand here the term problem in the very literal way that you have some, like, you're in some situation that is uncomfortable or something. Not that kind of a problem. It's about like you have some need of sorts and you wanna solve it. This is still very abstract, so that's why I thought the best way, and see, this is ultimately what I want to achieve with this course, giving you like good examples in an easily approachable, to the point language. Because having also gone through university, I felt that oftentimes you are given like very, very formal descriptions and explanations of things that at the end of the day don't really help you. And then later on the job, for example, or when teaching the stuff myself, then only I realized, this is what they meant all the way along with problem solving, because it's a very abstract term, right? Problem solving doesn't really tell you anything. So the to the point explanation is we want to automate some sort of a process. There's probably 100 different other ways you can define this. This is also not a formal definition of what a program is, but this is my definition, and I think is something that's going to make it understand at least. So we have some sort of a process, and I'm going to give you some examples now that we want to automate for some reason. So automate in this case just means you write the program once, and then you can execute it as often as you wish. That's ultimately the beauty of programming, right? So if you have the very first example that I would usually give is if you have some task that is tedious when done manually. We could as a very easy example, we could, and that's why I put, you might have guessed it already, the ATM at the side. So all the examples, or most examples, I'll try to make around this. So it's an automatic teller machine, a TM. So if you would have a bank teller back in the day, or still nowadays in some cases, that would give you money, and you can give it money in most cases for your bank account. This is quite a, depends how you see it, but arguably quite an annoying process, right? You just sit there all day, get money, it's dirty, you count it, you miscount it, and your boss slaps you on the wrist, and the customer as well. So it's a tedious task. Of course, there's even better example of stuff that is outright horrible to do as a human, or takes you very long. So you want to automate it in a way that the programmer writes it once, and you can then first of all, the beauty is, of course, is digital, so you can copy it infinite amount of times, right? If you want to have multiple tellers in a bank, you just need to hire another one. In this case, you just put another machine. Of course, it costs money and stuff, but you get the idea. It's the software, at least, is reproducible for free, and without any work attached. It's literally copying a file as you do all day on your computers. That is what automating ultimately means. You write it once and you can execute it infinite amount of times apart from of course there's costs involved and stuff, but apart from the obvious cost, you don't have to pay anyone to run your self-written software. The next example is something that can be done quicker by a program than can be done by a human. Also, perfect example here is the bank telling, right? If you say, give me very precise sum of money, obviously, you can all agree to that, I guess, the ATM is going to be faster in giving you this exact amount of money compared to a human starting to count. Even if they're very experienced, it's going to take them longer than the ATM doing some crazy quick sorting or getting the right bills and stuff. And even the better the ATMs where you can put money into the ATM and it deposits into your account, it's a lot faster at counting than any human could be. The next thing I already alluded to is that it can be done more reliably or accurately by a program than a human being could be. The teller again. As I mentioned, you might get a slap on the wrist from either customer and or boss if you do miscount the money. If you programmed your ATM software right, that's not going to happen. Of course, there are problems that you all know from using software probably all day. But if done right, then it will never miscount. So it's a lot more reliable than a human that will ultimately make mistakes. An important aspect here also is replayability. So what that means really is that you have sort of a recipe. That's already what I mentioned earlier with the write it once and run it infinite amount of times, right? That's really the beauty of this. If you would think of a more manual physical process like creating some like a hammer, let's say, many parts of this nowadays are made with molds and stuff, or not nowadays, since many years already, obviously, such that you can make it replayable. So you make the mold once and you can just get the exact same hammer every time. All right, the next thing is that it might be something that can be simplified by a program that is otherwise quite difficult to do manually. Not necessarily tedious work, but just something that is simpler when done by a program. There, I don't have a very good example. Oftentimes, this is about certain workflows that you have something that if a human does it, it involves steps A, B, and C, and D. I know this is sadly very abstract, not so good example, but yeah. And if you program it properly, you might be able to skip certain steps and stuff like that. That does happen quite a bit, that at the end of the day, the workflow actually is easier on paper in the program than when done by someone. An important fact is that it can be scaled easier. So I already touched upon that earlier with this whole replayability thing. So if you have something that doesn't even involve hardware, if it's a sole software thing, so just displaying something. I mean, of course, that involves a display, but I mean that is compared to the cost of an ATM, that's low. So you can scale it a lot easier than having a human do that. Yeah, that is very often a good reason to put something into a program. Important, of course, it doesn't have to be something that always is done manually. It can just be something, of course, that you simply don't do yet manually, because you already know that any of these bullet points would hit. It's for example, it would take you forever to do as human. Many tasks you do in a program are outright so difficult to solve, if it's a complicated mathematical problem, for example, that you're not even going to consider to hire someone and do the calculation on paper, or even with a pocket calculator. You're going to outright do it in a program. And finally, something that is a reality, of course, so I figured I should mention it. It might be cheaper to let it be done by a program. I guess an ATM is a perfect example here as well. You're obviously, I guess that's quite clear to everyone, going to be paying more if you hire 3 bank tellers for your branch that literally just accept and pay out money from the customers. And instead of once buying 3 ATMs, putting them in the branch, and even being able to run them day and night, which you have to pay your employees quite a lot for. It is sad, many people would say and would argue, but it is what it is, and I just figure I should mention it. For certain jobs, I think everyone is probably happy that the human does not have to do it, either because it's very dangerous or because it is very tedious, and you're not going to find very many people that want to do that if they're not forced to. That also frees up that more people do stuff that actually brings them enjoyment, hopefully. That's the utopia, but I figured I should mention it. That is very often a very good reason in like the real world. Yeah. Just quickly now, we're going to touch more on it in the chapter 1, but I quickly want to explain like roughly what does a program consist of and how is it executed. This is a super high level explanation, but I think without having understood this, none of the other things I'm going to explain to you, and specifically if you want to try it yourself, which you should, is going to make any sense. So the starting point always is human readable source code. That is ultimately also what is a program. It's just text at the end of the day. It can involve, of course, other things, but at the end of the day, it is text. What does source code mean? So it's just instructions, really. It's just you write instructions in a certain language, which is then your programming language, that will lead the machine being here like a more abstract term for a computer, because you might also have something that is not traditionally really a computer that runs it at the end, that you instruct a computer in what to do in certain situations. So you have usually some trigger that something happens, and you encode. That's ultimately where the term code comes from. You encode, you instruct what you do then. Oh, sorry, what the computer should do then. And human readable, that's the important part. So it was originally written by a human. Also, you being able, with the fact that it's a language after all, just as any other language, someone that understands this language can, in theory at least, pick up any source code written in it and start reading it and understand what is going on. And actually, if you do this as a daily job, you do read quite a lot more than you actually write code. That's just the reality of it. So the fact that it's human readable is the important property here of a program. What happens next is, I'm going to make this very abstract, because it's literally its own university course in itself. What happens next is that your computer, or ultimately the processor of your computer, sort of inner core, cannot execute human readable source code, because first of all, there's way too many programming languages to be able to do that. So you need sort of a lingua franca if you want to. So some other machine readable language that is very abstract and very basic, such that your computer can execute it. So what the next step then is that you take your still readable, human readable source code. Source, by the way, I didn't even mention what that means. So this is a bit of it doesn't really mean a lot. What you just mean if you say a source code is that it's the single source of truth. What does your program do? there's many ways, for example, to then convert it into something that your computer can read, but this is like the starting point. That's what source conveys. Yes, next step is that you run it, and these terms might or might not tell you anything, through a compiler or an interpreter. We're going to look in the chapter 1, what does that mean? Just take it, the terms as meaning nothing to you, or maybe they mean something. What this ultimately means is a translator. That's what you can think of it like a human translator that translates language A into language B. What a compiler and an interpreter in different ways do is they translate your human readable source code into machine readable, and we usually then call it compiled code. That is not human readable anymore. It is to an extent, depending on what your machine readable code looks like, and that's why it says here there's very many nuances to this. It is still readable to a human, but it's not really usable anymore. Like, it's in a very abstract form, such that it makes sense to a machine, and that machine can execute it efficiently. What that ultimately means is that it's very many basic operations. So you would get from like a very, very like grandiose program that does a lot of things to, in the end, just very many arithmetic operations, of course, just summing things together and stuff, and temporarily saving somewhere else, and then jumping somewhere based on certain conditions, etc. But nothing you would really want to code as a human, although that does exist as well. But what you should take away from step 2 is you take human readable source code and translate it into something that the machine, the computer, understands and can execute it efficiently, right? That's ultimately the goal. The output of this is what usually is called compiled code, is then usually, but that depends a bit, packaged into something called, you will hear terms artifact, executable, binary. I will still come into what that means. Format. Essentially what it means is you usually don't put, if it's not a super small program at least, you wouldn't put all your source code into a single file, because at the end of the day it's just files, just like a Word or Excel file or whatever. You wouldn't do that with a larger program. You would split it up into multiple files, and that's ultimately what you do in the development and engineering part. It's not just programming. So structuring something properly. You would bundle this together in some way or form. So this is what step 3 just means. You bundle it together into one package, really, such that then later when you share it either with your colleagues or people that bought the software from you, they can just run it. A very easy, good example for this is actually some off-the-shelf software. If you take an MS Office or any other such program, like Word, for instance, you're not concerned as the customer about how does this do what it does. I'm concerned about that I can write my text in it, and ultimately what you want at the end is that you double click on some icon and it just runs the program, right? Runs the software. So that is ultimately what all these terms refer to. That is not required. That's why I say usually. You can not do that, depending on the language, on the platform where you run it. A lot of things, not going into detail now because it's too much for this. But this is something that usually, at least for larger projects, you would likely do. But you can skip this step in theory outright. And then finally, the very obvious last step is that when commanded to do so, your operating system, so what runs the process on your computer, spawns a new process that runs this code in its machine readable form on your processor. So it just takes what came out of step 2 or step 3 if you had that as well, and it executes it. This is also a bit of an abstract term, of course. What it essentially means is you go through all the instructions from top to bottom, and of course you do jump around if certain things happen, like as I said with these triggers, if this happens then you might do that. So it's not like a sequential thing necessarily that you go from top to bottom always, but in essence you do that. You start somewhere at the top and the computer runs through each instruction and does something, whatever you instructed it to, and that you see in some way or form. So it can be output on your screen, it can be that it just does something internally that you don't necessarily see, but it did happen. So save a file, for instance, or it's nothing you physically see or something. It's just you have to trust that next time you open it, it was indeed saved. So yeah. So that is what when we're talking about execution. So it's about taking your written code in its machine readable form and letting the processor go through it step by step and doing the instructions you wrote beforehand. Yeah, that's that. I want to end this first chapter with, as I mentioned earlier, some terminology, since it is very confusing part of this whole thing. And here's some few basic first ones that you're going to encounter a lot. My plan is, I think, to do this also in the following chapters, if there is some need for terminology being explained, then I'm going to do it at the end of the chapter. So we're going to start, and I think this actually we can skip already, with source code versus compiled code. So this really just means you might also read binary code sometimes for compiled code. This just means that source code being human readable code, compiled code being code that the machine, your computer, your processor can read and execute actually. The next term that is very close to this and also very important is compile time versus runtime. What this just means is that you have a step involved, and this differs again a bit on the exact setup, that does this compiling. For now, think of compiling as translation, and transformation also oftentimes. That does this compiling into some other form, other language, other format, and then the runtime. So compile time refers to the fact of I'm done with writing my program, or I just want to try it out, right, and want to run it, and I do this translation step versus I run the program after it has been compiled, and it's actually running, and it can do something and it can crash. Of course, that's an important part of this. There's a lot of importance about these two terms that we'll see in later chapters, but keep what they generally mean, you know now. Then about all the terms of the occupation, the job. You will hear programmer, a coder, also very common, coding as a verb specifically. And then if you look more into job descriptions, maybe software developer and engineer. Of course, there's bazillions of other more like precise terms that describe something. There's no room to even explain all of them here, because some of them are I don't even straight up understand. But what this all essentially means is the same thing. There's very many nuances as to everything, but it essentially, for your understanding, right, because you're starting and confused, what does this mean? The general distinction that you can make is that, and not everyone agrees with that, but that is something you will most often at least find, is that programming and coding essentially refers to the task. And then obviously a programmer and coder are people that do this task. While software development and engineering, even more specifically, refers to a lot of things around just the craft side of things. So how I would describe it usually is something, the example I gave a bit earlier already, is a good, at least a starting point of an example. There's a lot more, of course, but we're going to see later, specifically if you think about what is software engineering, because it's a lot more than just coding. A very good example for your understanding is if you think about I now know how to write code, how to program. But what you would also want now is that you can give it to someone else that you also know that knows at least the programming language that you wrote it in, and they'll be able to understand what you wrote quickly enough. We're going to assume they know the language well enough. That's not going to be a language barrier, if you will. But what happens, at least if you start out, is that you structured your code in a way that it does do the right job. Like, it works perfectly fine. There's no issue with it. But you structured it in a way because you just didn't know any better, obviously. That is very confusing to other people, and made sense when you wrote it, but maybe to yourself, even if you read it again a week later, it's like, what the hell did I do there? And that it might check all the boxes on paper, but it's what we typically call maintainability. It's not maintainable a lot. And that is one of the cornerstones of what developing and engineering is also more about than just the raw crafts thing. It's about how do I do it good? How do I do it correctly? How do I verify that it is correctly? All these topics that are not just about writing it and forgetting about it and just running it somewhere. That is typically the distinction we will have between programmer and coder, which I would generally say is the same thing, and the more nuanced developer / engineer. And then in engineering, there's even more things, but we're not going to cover that. Also, separate video. Next is something, of course, you also hear all the time. I already alluded to software, hardware, which I guess everyone already knew, honestly. Program, algorithm, implementation, all these things you'll hear oftentimes. What I would generally say here is that software refers to something I forgot here actually is application as well. You also hear oftentimes. Software refers to just very abstract term, a piece of coherent program or multiple programs oftentimes that do some like task. And usually that's like a larger suite of tasks that what you would call software. So if you take an ATM, it cannot just do a single thing. It's not like that's why you have like buttons and stuff, right? You can choose in a menu, I do this, I do that, blah, blah. That's what I would call software. A program is it's the smallest unit of that. So one part of this that just does, for example, counting the money. That's what you can consider a program. Program in general is also used for just the raw like final product that you in the end execute. So this step of converting it from source code to compiled code and then running it, this is what many people would also call a program. So for example, you often hear, I'm using MS Word as my word processing program or software. So these are a bit interchangeable. Software is more abstract, like software also what I would refer to as a whole suite of things that do a common task. This is a bit abstract. You cannot really define this nicely. What you can define a bit nicer is algorithm. So what that refers to is that you, on an abstract basis, you have some instruction of something you want to do. The very easy example for this always is you want to sort something. That is like the go-to thing for algorithms, which we're going to also look into a bit. So you have like a recipe. I think this is actually a nice way to call it. You have a recipe of if I want to sort. Let's take a very easy example of you playing cards. So you're playing cards with your friends. You all do if the game needs it at least, and many of course do. You want that your hand is sorted. So you want that the lowest numbers are at the beginning and the higher is at the end, such that you can play a bit quicker and you can make better decisions and beat your friends ultimately. And the way you do this, probably there's probably different ways of doing it, but there's a recipe you follow. Very likely, I'm very sure that you follow this, which is that you start at the top or the front or the back of your hand, and you take the card out and you go through all the other cards and see where does it fit into, right? So what other card? So putting it between two cards that the other card is lower and then the higher card, the right card is higher, or maybe the other way around. I'm pretty sure in countries that read from right to left. I guess you also sort the cards other way around. Not sure. Would be nice. Put it in the comments. Actually, it's interesting. I don't know. I do it from left to right as I would read English or German. That is, you could argue that is an algorithm. That is a recipe because you follow a very clear pattern all the time. You take a card, put it in the spot where you know it is roughly correct. And if you do that often enough with other cards, your hand is sorted, right? And I think that's a very easy, very good example for what an algorithm is. Because what is important here to understand is that there's no code involved in algorithm necessarily. It can be, but it means just on paper, a description, a recipe of how to achieve a certain thing. Sorting is a very good example of that. Of course, there's millions of algorithms to do anything really, but it's my point being here is that it's an abstract thing of just the way to do it and not necessarily the exact the exact the exact way to do it. I cannot think of a better way, and that's where the next term comes into play. Actually, the implementation. That's why I put them next to each other also. So you might have an algorithm that is very abstract and just like in an abstract form describes. You take a card, you see where does it fit, you put it there. That's the algorithm. The implementation, and that's something you also read oftentimes, is how to precisely do this in program as source code. So there you would have things like, think about it. If you would have a game where you can play cards, of course there's plenty of solitaire and poker and whatnot, computer games for cards, playing cards. How would you actually do that, right? And that is the implementation, that you have some representation in your program of the cards, and how you actually do the sorting. That is what the implementation refers to. So there can be different ways, of course. You can implement the same exact recipe for sorting in numerous ways. You can make it a bit better, a bit worse in terms of speed, for example. You can optimize it and stuff like that. But that's what implementation refers to. Finally, since I thought about it just a second ago, is application. You specifically, since the first iPhone in 2007, I believe, came up, the app. The app is a very common term that you hear all the time, referring, of course, to application. This is also abstract. I would mainly put it in the same corner as where I would put software, even though it's a bit more tangible. So application is like one distinct program that you can run. Nowadays, people call everything application. This also, the word changed a bit over time. I think this is usually the best way to describe like one coherent piece of software that does something. So your MS Word, I would probably call that either a program or an application. And then the class of word processing, that I would call software. So there's like LibreOffice, MS Word, OpenOffice, StarOffice, whatever else Office there is. All of these I would call like word processing software, or whatever other tasks they do. And then the exact MS Word, I would probably call that an application. This is a bit debatable, but that's my definition. Next one is languages. You probably heard the term programming language, I'm pretty sure. What it refers to is, you can imagine. If you cannot, it refers to one flavor of a way to encode, and that's where the code comes in again, to encode your ideas. So you need, of course, just as you need to human and natural language, as you would correctly call it, to share your ideas and also instructions, right? You have you use instructions all day to tell someone, could you please do this, or be a bit more strict, do this now. This is essentially what you do with a programming language as well, and in the way that you can do it with the human natural language. There's different flavors of it. So there's various hundreds, thousands maybe, of languages to achieve very similar things in different ways. Some work on different principles. So just as you have languages in natural languages that work differently on the way they form a sentence, exactly the same you have in programming language. The analogy here goes very good actually between what you understand on the term language. Then what you also hear, and I quickly only want to go through this, is scripting and markup language. Honestly, scripting and programming language, there is nuances to this. For the time being, I would treat it as being the same thing. There's, I know people will fight me over this, but for your understanding, given where you start now, I would just treat it as the same thing. Ultimately, a script just refers to, as you have in a script, in a play, in a theater, refers to also instructions. So you say, you write down, based on certain things happening, what the program should do. That's what script refers to. And a program ultimately is the same. There's slight differences. We can cover them later. But for the time being, I would treat programming language and scripting language as the same thing. You also hear them used interchangeably a lot, honestly. What you do not hear used interchangeably, well, you might, but wrongly, is markup language. What that just refers to is not telling the computer instructions. If this happens, then do that. But instead, you you just describe like a static constant thing. So what thing? Sorry, that was a bit. So what you usually use this for is having some user interface. So if you have your MS Word, again, I'm using that all the time. I don't know. It's probably something everyone used of you, so that's why I keep using it. If you have that, that can be done differently, but at least historically, you will oftentimes would use the interface or the buttons you click on. They have, of course, interactivity. So you click and something happens, right? That is, of course, code programming language. But the fact how the button looks and where it is positioned on the screen, this is typically what you would do with a markup language. There's very many different other ways of using a markup language, but what you can remember off of this is a markup language is something that there's no instructions. You just define something and it's static. That's the important bit. Yes, then a term I'm sure almost everyone already heard is bug versus an error maybe also. Bug just refers to a behavior of your program that is not intended. So it does something that actually you didn't want to, you didn't mean to. It's so bugs in itself are not purposeful, such that, I mean, there's actually a few examples where people do this purposeful, but in the general case, it's something that happened and you didn't want to. It does something that you didn't intend to. The term, just for because it might seem weird, the term refers to when computers were the size of an entire house or a room. Refers to the fact that you did have the problem that there was literally bugs, so like some critters walking around inside of these huge, large room-sized computers, and if they stepped on the wrong electronic components, just as you can imagine nowadays in a larger, everything is so tiny nowadays. Like if you imagine a larger TV, like a CRT, there's a lot of electronics in there and of course a lot of current on everything, power. So if the bug stepped on the wrong thing, it might create a short circuit and just in the better case, let's say, just cause some behavior that the programmer didn't intend to. That's why it's called bug, and it's just a really factual reason. Nowadays, of course, that's not going to happen anymore. You can still have a fly that lands on your computer insides, but usually, first of all, nothing will happen, and secondly, this is not the usual case. But the term stuck, or if it's even worse, you might get an outright crash or something. You might hear bug and error used interchangeably. Usually, though, bug refers to something that is unintentional, and error is just the fact that it happens. So, like, the bug you say is like the description of what do I have to do to cause this problem. So, usually a bug is if you have an exact setup. If I click, for example, in Word, again, if I click these two buttons these three buttons in the exact order within 10 seconds, the program crashes. And you all know these things, right? Happens sometimes. That's a bug. And it has a very clear description actually how it happens. We don't necessarily know always why. That's also a big part of software development. And that's actually a good reason here, a good example here. That's what I would not call maybe programming. This is very clearly software development. Fixing or getting rid of bugs that someone else or yourself discovered. And the error is just the effect. So you would say the bug is I click these three buttons in the order and it crashes. That's a description of the bug. And even better if you have a more precise description of why that happens. And the error is it crashes, right? So that's how I would usually use it. The second to last thing here is editor versus IDE, which stands for Integrated Development Environment. You will hear these terms a lot. It just refers to the program, funnily enough, that you use to program your own programs. So you, of course, since it's written text at the end of the day, you need something to type it into. That I guess you all know. So there's just specific programs to type your source code into and then execute them. Editor usually just refers to just a plain a box essentially where you can type into and save it and load again, and it doesn't do a lot. And an IDE refers to in the core an editor, so just also a text box with a lot of extra things. So this is very there's a lot of subtleties to what an IDE can and is. What I would imagine is it's a like powered up or improved editor, let's say, for the sake of developing. Because the reason really where the difference is, where also the development environment comes into place, that with an editor you could also write a book in theory, right? It's just a text box. If you write your book or an essay for school or whatever, you can do that in an editor. As a matter of fact, Word in itself is an editor of sorts. But you wouldn't want to program in Word. That's pretty painful. While it does work to an extent, no one in their sane mind will do that. And then with an IDE, you have a lot of extra features, such as automatically detecting bugs, for instance. There's certain things that the IDE can already tell you, hey, buddy, here this will cause bug X. And that's something your general text box editor will not be able to do. And so I would generally recommend to use an IDE, but of course there's a lot of discussion over this in the community, and people prefer different things. But yeah, that's really the description. And finally, syntax versus semantics. So what this just means is also terms, as you may know, borrowed from linguistics, from natural language. So what it just refers to is syntax being the way, how the language is written. So the fact what signs are legal, same as you have in the natural language. For example, I might say in German you can use Umlaute, so the funny characters with the dots on them. Also many other languages, of course, have different accent characters. And in English, for instance, you don't have any apart from a few borrowed words. But in general, in English, you don't have any. So this would be a syntactical thing. And then semantics thing is the meaning. Well, that's how you use semantics, I guess, after all. So if I have a sentence that it adheres to the syntax of English, for instance, so it starts with a capital letter, ends with a full stop, period, and has the correct like syntax in the middle, so the way the words are formed. Then the semantics is what does it actually convey? What does it mean? If I read it, what do I get out of the sentence in terms of meaning? And interestingly, this is one-on-one pretty much transferable to programming languages. So syntax means how do I write a program that the compiler at the end can actually translate it, transform it into machine-readable code. And the semantics is what does it actually do? Like, one thing gives you money back, the ATM, the other thing plays a game for you, right? That's the semantics. Yeah. That's it. I would ask you if you either didn't understand any of these or have another word that you read somewhere and you wonder, what is this telling me? Or you Googled already yourself, which of course is recommendable in general, and it still makes no sense to you, which is very probable at the beginning of this pursuit to learn to program, then please post them in the comments. I'll be happily responding, trying to answer this stuff. And so I would ask you to do just that. That's it for the final. For the final, it would be nice, right? But no, for the first or 0th chapter, the introduction. Quickly, some final words, and then we're done here. Again, keep this sentence here that you already saw earlier on the objective slide really as the creed or whatever of this course. That's what I ultimately want to achieve. There's obviously not going to be any homework or anything. It's not a formal education here. So do it in your own speed, in your own time, and do it such that it stays fun. That's ultimately important. That's also, I would argue, the main reason why you first of all keep at it. Of course, as with anything, if it brings you enjoyment in some way or form. Fun is maybe not the right word. Enjoyment, I guess. Or satisfaction, then ultimately you're first of all gonna learn quicker because it's gonna be more interesting to you, and I would also argue you become a better programmer, developer, engineer, wherever you want to go at the end, with more enjoyment. So if you do realize at some point, this is not really for me, then honestly, just either finish watching the chapters, the course, and just have it in the back of your mind for when you do encounter this again somewhere. Because I mean, let's be frank, software isn't everywhere nowadays, obviously. Or you might just say, okay, this is just not for me. I'm gonna do something else that actually brings me fun. So yeah, but also something else is don't give up too early, right? If something seems a bit either difficult to you or straight up boring, maybe try stick to it and at least finish the course, and then at the end see if it is still the same. Because I have to say, as one says, I'm not sure how the saying goes with the hunger comes while eating or something like that. I'm not sure what is in English. We have this in German at least. This also goes for many tasks, obviously, but also for programming. Starting is not the biggest fun oftentimes if you're not super curious as a natural character, but being able to later do, like, you have an idea to do something and you just being able to do that, to implement it yourself, is pretty magical and a super nice like skill to have, I can tell you. And of course a nice job career path. I mean, if you want to develop anything, applications, games, something. So some final words. I would encourage you to either become and or stay curious. So I think this is ultimately what, as I mentioned, will lead you very easily, very naturally also to become a good programmer, and also to get there more quickly, really. Then the next point is to research for yourself. What I do not want to imply with this is that you do need to read some other material, like you might have in a school or something, that you're being told, oh, read the chapter blah 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 of this book until next lesson. I'm not trying to do that. If it is really required, I will tell you to. But the course, I will definitely aim for it being self-contained, that you can just watch it from beginning to end, and it'll be clear. However, what I do mean by this is that I can recommend in general, is really more of a recommendation than really a requirement or anything, to start doing that, since after all, this channel is called the Self-Taught Software Engineer. So if you arrived here watching this, you already did the first step, right? You found this somehow, which is researching, right? So I can only recommend, if something is unclear, do one of two things. Either start researching for yourself, which if you do if you did it a couple of times and you know how to find information well. And honestly, I expect, I guess people that grew up like in the 2000s something are probably also better at this in general, because you grew up with the internet. That you either do that, and I can just recommend it, because I don't know, that's how you're gonna accelerate. But also, of course, ask someone else if you don't understand something, because the issue with researching, after all, is that it's hard to find like good information or like the right information for what you're looking for. Oftentimes you might see like some term being used, and as I mentioned earlier, you start Googling it and you get some you get a lot of results, very likely, but it's all stuff that you're not going to be able to understand. So this does come with an asterisk of sorts, but just the raw fact that trying it out, I think, is something that everyone should keep in mind. Yes. Something else I'm gonna offer is that you can reach out in the comments under each video if something is unclear, and I will try to answer them. Of course, it comes with time. I mean, this is for free. You're not paying anything for this, so I do have a day-to-day job, and I do just since I enjoy doing this. But I'm gonna try to answer everything, and keep posting, I would say. The next step really is a continuation of this. Be gentle with me here. First of all, this video actually is the first video that I'm doing in educational sense. I did teach before, but didn't record any videos. So please don't be too harsh with me, but give me feedback. That is that is what I would want out of this point. So yeah, if you have some feedback points of stuff you would love me to improve, stop doing, start doing, also continue doing, of course. I'm happy if it's positive feedback, but please, if something annoys you, shoot it out to me in the comments. I will try to improve that. My point is just that this is the first one. If it feels super shit to you, then please comment that, but also understand that is also my first try for myself, right? I'm improving it. I'm improving it as we go. And finally, try out what you see in here. Like this really is ultimately even more importantly than the curiosity and the knowing how and when to research part. This is really what I also would consider a big part of being of trying to self-teach yourself, or being self-taught, to try out what you hear. After all, as I mentioned, the point of this course and many parts of programming and software development are very crafts oriented. So you can do a lot of things with your hands. I mean, even if it's just obviously typing on a keyboard, you can do something. It's not something where you necessarily have to do like a thought experiment or something, as you might have it in other sectors. So this is really the thing I want to encourage you to, and I'm gonna show in a different video how to like set up your home computer in a way that you can actually do that, because of course I said try it out, but you have no idea how, likely, or maybe. So now in the top right corner, I hope I will link a video where I go over on the example of the Kotlin language again, how to try this out. So my point, as I said earlier, and that's how I'm going to close this first chapter, is I'm going to try to make it such that you do not need to let's say the things you learn in this course are applicable to ideally any programming language, or at least a wide range of general purpose ones. But I will give them on the example of the Kotlin language, which means, of course, that all the examples I'll be giving, either I'll do them very abstract, such that it can be applied anywhere, but if that is not possible, which will happen at some point, because we just do need to show you how something works, or what it would look like if you would program that. I will do that on the example of the Kotlin programming language. So for the fifth point here, I can of course recommend to install that on your own computer or laptop, and if you want to follow along, and as I mentioned, I can only recommend to follow along. It's not a requirement. You can just watch these videos without doing anything, and actually that will probably bring you quite far, depending on what type of learner you also are. That also depends a bit on that. But I can recommend and would encourage you to just tinker around ultimately. It's not even that you just type what I'm typing. That doesn't really help you. Just like try out some stuff. I showed you in a chapter how you do how you loop over a collection of things. Well, just make a collection of things yourself. I will give you the instruction how to do so. That's something I'm offering you. How to do that, and then you can try it out yourself and do it with, for example, different examples than what I did, and try to explore a bit the possibilities of the language, and on a broader scheme of the crafts of how to program software. Yes, that's it for the first chapter, the first video. Thank you very much if you made it all the way here. Final remark again, please give me feedback. This might have been quite lengthy to some people, maybe not. I really have to strike like a nice balance, so please, about the length, but anything that comes to your mind, leave me a comment when it comes to feedback. Thank you very much, and I see you in any of the next videos. Either I can recommend to watch the one where I introduce myself and give a bit of context about this channel, or the one how to set up your local environment, and then of course finally the chapter 1, which is the basics of program execution. See you there. Bye bye.